So good morning. It's a real pleasure to be here. Over the years, I came quite often to the Nordic countries, so always a pleasure to come back. Obviously, through the session, really don't hesitate to interrupt, raise your hand, ask questions. It's great for me because then I can adapt to the audience. I've been told that there is a wide diversity of backgrounds, so I'm going to try to adapt and have content for everyone. If you are less familiar with the technology, if you are less, let's say, working on the core access metro aspect of the designs, the presentation is built to give you the key concepts. And that's basically what you should just focus on, getting like an intuition for what this is. The exact details of the ideas, if you are not familiar, it's not so important. What is important is the intuition, really the philosophy of the solution, because it's very different from previous solutions. And with the intuition, then I think you will understand whether this is applicable to you, and then you will maybe talk to colleagues, and you have there are books, etc. It's largely deployed, so you can find lots of materials, maybe from your colleagues in the industry, for example, that have explained their use case. And from there, you basically can then grow your understanding based on your use case. So really is focus on the intuition. If you cannot follow everything, that's not a problem, okay? The key theme of when I started this project is simplicity. So that's very important for me to underline this. All of this is built for simplicity and for applicability to real use case. So once again, if there is something that you cannot follow completely, don't worry. Try to just get the intuition, because be really ensured that behind this, we really simplified the concepts and automated them. And so with then your study, you will find this out. And obviously, all of this has been designed with lead operators. All of what I'm going to present is deployed. Up to now, we started the project in 2012. There is nothing that we design it. There is nothing that we productize that is not deployed. And for me, it's a metric of success. Because what I did not like is all of these features that are not really well thought, and then there's overlap, and then this is not well engineered, and then you need to hack it after. Well, up to now, we have nothing of this. And so everything is deployed. Why? Because everything has been engineered with lead operators who had the use case, and then they deployed it, obviously, because it has been engineered with them. Okay? There are two sections in my presentation. There is a presentation first on MPLS, because this is where I started the project in 2012. The idea is segment routing is an IP-based solution. And so it applies to two types of data planes. It can apply to the MPLS data plane, or it could apply to the IP data plane. The MPLS data plane could be reused immediately without any hardware change. And this is where I started, because obviously it's easier to introduce something where you only need to have software upgrade. That is obvious. Then, in my mind, I always had the IP applicability, the IP data plane. And so, but there I needed hardware change. And so in 2012, it was way too difficult already to get this done for MPLS, so I focused on MPLS. Around, quite immediately, 2013, 2014, we issued the first proposals for the IP data plane, but it's more, let's say, at a research aspect there, because we know it's going to be difficult. And we really started the IP data plane with the lead operator kickoff in January 2017, 2 years ago. And you will see the picture later on. And so now we just announced our first deployment. And so the second part of my presentation is what is called SRv6. So same exact solution, but relying on the IP data plane, not relying on the MPLS data plane. But the philosophy of the two are the same. And I'm equally committed to both. That's why when I present, I try to do 50-50. Here, because the background is diverse, I believe it's easier to understand via MPLS, because you can feel it applies more to you because you think, it's only a software upgrade. So for that reason, I'm going to explain, take more time on MPLS, but really think about this as like really two instantiation. If you ask me, if the question comes up later on, Clarence, do you think I should do SRv6 or I should do SR MPLS? My answer will be, I don't know. It really depends on your use case. It depends whether this is an existing network, where you want to extend it, or whether you have a massive investment for 5G, and this is, there's not a green field, but there is massive investment and new generation. What is your prospect? Is it an end of cycle type of evolution, or is it a new cycle for 5–10 years? All of this take into consideration to understand what is the best solution for you. But the philosophy is the same. Also, obviously, because we have so many deployments with SR MPLS, we'll review this. Quite a lot of our deployments are now looking at SRv6 and are saying, wow, I'm really interested. If you project yourself at, let's say, an horizon of 5 years, I believe SRv6 is obvious. And so then our commitment is very clear, but since the beginning, is that for us it's a single solution. And so in the same way that we had a totally seamless migration solution from classic MPLS to SR MPLS, it's well documented, it's the first thing we released. It's called Seamless LDP SR Interworking. We have the same migration or interworking solution from SR MPLS to SRv6. Okay, so really, there would be much more that one we can say this morning. But again, don't hesitate with your question. It's really welcome. If I think that I will better answer it later on, then I ask you, I put it on the stack, and then later on I come back to it. Okay? I go through this first slide. It sounds marketing. It's not marketing. It's because when something is new or novel, especially with a diverse audience, maybe it's the first time you're going to see this, you might think, oh, that's blah, blah, blah. That is PowerPoint, that is far away. So I go through this to have a reality check. It is now not at all blah, blah, blah. It's largely deployed. So the industry backed up segment routing in a significant way immediately. So I first presented this at a Cisco private event with operators in 2012, October 2012, and we immediately formed a lead operator group. We went to the ITF in January or March of 2013, and then it started from there. We had the first product in 2014, and I think the first deployments by the end of 2014, beginning of 2015. From there, we can no longer count because there's been so many releases that now people upgrade the software, they do the migration, and even the account teams do not report it to us. So it's difficult to count how many deployments we have. It's well over, I think, $1 billion of business impact, which is very important because it means that there's been a lot of investment, and the investment is really significant. So the customer adoption is in any segment of the market. That is important. It is in web, OTT, it is in service provider, it is in the enterprise, but it is as well in any segment of a network. In the data center, we have deployments that are public. In the core, we have deployments that are public. In the metro, in the access, we have public deployments. And more important than this, because that's the initial goal that I had, this is designed as an interdomain solution. So we have public interdomain quotes, press release, which is always important for you when you consider solution, because then you can contact the operators, you can check the maturity and discuss the experience with them. When I started this, one of the trigger points was reading the SDN, the first major SDN experiments that were 2 SIGCOMM papers from Microsoft and Google, respectively the SWAN paper and the B4 paper, that were really, I think, extremely good paper and extremely good research. And more than research, these people actually deploy networks on the basis of their study, which is really brilliant. But reading the paper, and I say it because I would not want to sound like saying these were bad ideas, not at all. the idea that they had was that using the tools that they had, they basically invented OpenFlow and show how they could build an SDN network with OpenFlow. And this is brilliant from a realization viewpoint back in 2012, 11, maybe 10 time frame, because they started much before they published the paper. But if you look at it from a network-wide side, there was a major flaw in the OpenFlow idea, is that this big controller would program all the fib entries of all of the routers for all of the flow. And obviously, if you are a bit into routing, obviously they can be super good and they could resolve problems that the network industry has been struggling with. But no, there's really something unscalable with that approach, is that the level, the building block on which they were basing the idea, which is a single fib entry for a flow on a given router, even worse than this, even on a line card basis, is very, very small, too small for the controller. The controller does not need that level of, and on the other side is going to struggle with. So the idea was to say, no, we would need to control the network with a block that is much bigger than this, which is a segment that is instantiated, controlled, and maintained by the distributed routing protocol. And so we're going to have segments in the IGP that represent the shortest path to a peering point, a shortest path to Copenhagen, a shortest path to Stockholm. And so the network controller then no longer needs to go at every hop, but where he needs to instrument a specific path or a specific policy. And the shortest path, let's say, to Oslo, normally would not go via Stockholm, but another path, and you think it should go via Stockholm. The only thing you need to do is at the entry of the network, catch that flow, and in the packet header say, hey, you first go to Stockholm, and then you go to Oslo. And now that's the idea. That's really where it started, is to say you don't want to create state everywhere in the network, and you don't want to create state at the flow level, because it's going to explode the thing. The controller is going to struggle and lose time where there's no value. The routing protocols, they've been invented for 20, 25 years. It's a piece of cake to maintain a shortest path to Stockholm from a network-wide viewpoint. The controller doesn't need to do this. What the controller needs to do is understand which flow needs to go via Stockholm to go to Oslo and catch that flow at the entry of the network. And then it needs a technology to put that source route into the packet header. That's segment routing. And that's why, and that has been like a metric of success as well, it became the de facto SDN architecture. There are numerous papers and public statements from Google and Microsoft as well, showing that indeed they recognize that this was a superior way to do the SDN solution from a network programming viewpoint. Standardization is complete. We had the level of many RFCs being published, so it's completely done. Multi-vendor consensus now, it has been a struggle in the beginning, but this is over. And we invested a lot in having an open source ecosystem. So on the right side, from Bell to the right, these are the public statement of deployments, which is good because then you can contact them and you can see the use case, etc. On the left, they have not publicly said that they have any deployment, but there are many other people, but a few names, they have been strongly involved with the standardization. They have presented at conferences. And so if they do all this, it means that they're interested. This is one slide to summarize the idea of the segment routing solution. So first, seamless deployment. With the MPLS data plane, software upgrade, seamless insertion in an LDP network. With a provider, they're just deploying in 2018, and they did a lot of qualifications, and I think they're going to report, to write a paper to report how easy and how flawless the deployment went. So this is again an outcome of lead operator cooperation, because when we started the project in October 2012, The lead operator group was started in November, and from November to March, we only focus on the LDP seamless insertion because it's like black and white. If you don't solve that problem, you cannot get into existing networks, etc. And so we work at that time, I hope to remember everybody, but Bruno Ducran, Stéphane Litkowski from Orange, other people. And so we went through many ideas. And then around March, on a flight back from San Francisco, that's easy. And it's often like this. It's like BGP PIC or TI-LFA. You research for a couple, there it was quicker, but for BGP PIC it was a couple of years until, damn, it's so easy. And so then we found a solution in March 2013, and this has been basically the first product, the first software release, and we started to deploy from that seamless deployment. Interdomain is the day one target. Why? Because the idea of the source routing was to basically make the network fabric stateless. A very difficult aspect of the prior solutions for IP is that when you go from one domain to the other, you are faced with two problems. If you just want to have best effort connectivity, you need to leak routes or propagate routes, etc. So there are all sorts of either scalability or complexity approach that you need to have a continuous route from A to Z across these domains. With source routing, you don't need to. Your island can be totally disconnected. You just need to have a segment that brings you to a border. Once you're in the other domain, but the next segment is routed in the domain. That gets you to a border, and then you at the other domain, the next segment will be recognized. You see, you can completely decompose your routing. That is completely different from what has been done before. So that's one key idea, and that's for best effort connectivity, to decompose the route leaking so that you can take different approach. From a SLA viewpoint, from let's say a non-best effort, let's say the low delay target, it has never been done before. It's clear. I mean, already within a network, RSVP would not scale. Interdomain, nobody did it. Or if they did it, they claim, but most likely for fast reroute and without real traction because it's well known that it's super complex and it doesn't scale. So from an interdomain viewpoint, the SLA comes immediately because if the shortest path from one domain to another is let's say one path, but I believe that the low delay path would be to exit from France Telecom to Deutsche Telekom, let's say in Strasbourg, and then to go to Berlin via Frankfurt, I just encode it as segments. I control my path, and I see everything from my controller, so the interdomain SLA comes for free, and with the same stateless property, okay? Automated 50 milliseconds protection, there are two aspects to it. The first aspect is that as soon as I have source routing, I have complete traffic engineering control. I can engineer my backup path the way I want. So from a backup path instantiation viewpoint, I'm done. I can do whatever I want. So then I go into the theoretical problem, which is, what is my backup path? How can I compute in advance of the failure to have the best optimum path? That's the TI-LFA research. Took us a year to get there, but once we got there, it was again, oh damn it, it was obvious. But that's a good metric also to see whether we're on the good path or not. So if I remember well, TI-LFA was found in summer 2013 in a train station. It's always good to know because the first one is in a flight back from SFO, the other one is in a train station. You will see later on was in a taxi in Rome, never at the office. That's why I never do the offsite. I never go to the office. So I find it's blocking creativity. So I find it funny to share because it's always a bit interesting to see how projects go on, and it has never been done in the office. Okay. So this has been shipping in 2014. It's TI-LFA, huge amount of deployment. That's obvious. I mean, if you look compared to anything else, there's no comparison. It's just automated, simple, and that's the optimum. The next one is micro loop avoidance. Micro loop avoidance, Basically, in 30 years of IP, there's never been any solution to this that personally I would think would be working in deployment. So we've been working on this with the team for certainly almost 15 years. We issued a few patents because when you do research, you have to, let's say, to issue the patents of where you get to. But we never, I never asked or I never lobbied for productization because I was not convinced it would work. Or to the contrary, I doubt that the idea we had found would work in practice. Up to the point that we get to segment routing, we find TI-LFA, and then, microloop comes for free. Same solution. And that is, again, a metric of success. Because if suddenly a thing that you could not solve before comes for free, it means that there is a real capability and simplification that you have, and a paradigm that is fundamentally changed in the solution. Then you will see it's shipping and deployed. It's all the enhanced performance monitoring. Because if you look at traffic engineering, if you look at SDN, if you want to control traffic over your network, if you're blind, you cannot do it. What's the point of having a hammer, lots of tools? So yes, you have the tools to do it, but if you don't have the visibility, what's the point? And so the performance monitoring is basically to give you visibility into your network, which path have which property. And so it was obvious from the beginning that segment routing would basically have a big aspect into the performance monitoring, into the visibility into the network. And we'll come back to it with all the delay measurement technology. Then the next part, we said it immediately, and because it seems obvious, but segment routing is a unification of the infrastructure or underlay, the overlay, and the service chaining. It's obvious. As soon as you want to steer a packet through a service chain, go into that NFV there to get a firewall, then get there to get another NFV, and then get there. It makes no sense to create state in the fabric. It's completely stupid. So much easier to stack this segment routing extension header either as MPLS or SRv6 in front of the packet, and then get the packet to go hop by, not hop by hop, but segment to segment into this server to get this NFV, and this server to get to that NFV, etc. When I arrived this morning at where my colleagues were sitting, they have this little pig snort, I don't know how to call it, this little toy. I took one because it's one of the NFV applications that we have with SR awareness. So if you use Snort, it's SR aware. And so you just plug it where you want on Linux servers, and then it's SRv6 aware. If you want to steer a packet to it, you just place a segment, it will go there, and it will then go to the next segment, which is maybe your peering point. Nothing else. You don't need to create like an SH, new protocol state in the network, etc. Snort immediately is able to change the segment list. So for example, if Snort sniff that there is something wrong with that packet, and so the next segment, which is the peering point, is not what should happen, but instead the packet should be redirected on a different set of NFV or a different next segment, it changed the segment list. That's right away in the open source application. And then you tell me, yeah, but maybe I will need to do what you did for Snort, I will need to do it for all of my application. Not at all. We have 3 or 4 different types of proxy that are available in the Linux kernel and the VPP FDIO virtual forwarder to basically plug this in front of your legacy VM or legacy appliance or legacy container, and immediately they go into a segment routing network. You can do it today, it's available. Last but not least is the on-demand segment routing policy and automated steering. So this for me is, I think it's with TI-LFA the heart of the solution from an operator viewpoint, because it's the automation of the traffic engineering solution. So before, I think RSVPT has been a fantastic work 20 years ago, so only positive words to say to this. At that time, it's a brilliant piece of engineering at that time, but it became really complex and unscalable 20 years after. So there, the problem is tackled in a different way with simplification and automation, and we will come back to it because I want to cover it in detail. So this is in one slide, this notion of unified fabric. And so that's basically what summarizes the deployments we are seeing. Interdomain, core metro access as a unified SR fabric, stateless and simple, with policy. And then depending on what you want to achieve, you no longer need to leak routes between domains like what was done with BGP 3107. You can completely isolate your domains for scalability. It's always important to report achievement and milestones with the lead operators, because again, it gives you a notion of credibility, and then you know who you can contact to. So last year, in January, I first presented this notion of Flex Algo and all of the delay performance measurement that goes with it. And during that first presentation, Niels from Vodafone was there and said, it's exactly what we need. So in a year, we went to deployment. So it's shipping, and the deployment has been announced by Anton a month ago. He joined me at the Cisco Live conference to basically explain their 3-tier latency service. So it's based on the segment routing deployment. That was one of the first deployments, I think, back in 2015. And then augmented with the latest solution that has been released last year, which is Flex Algo, and that I'm going to explain in detail in the next few minutes. And this is basically allowing the operator to have 3 types of latency service in the network. One, which is best effort, described as the blue flow, so which means 1 and 6 are 2 access devices. And obviously between 2 access devices, the capacity is such that you go up through your core and then you go down to the other access, because that's where you have the capacity, where it's the cheapest to transport. Then on the other side, you have a minimization of the latency. This is obvious in the 5G type of evolution, that between 2 access towers, between 2 different access points, they're going to be fiber shortcut or path shortcuts, but these ones are going to be never dimensioned for all the traffic between these 2 access points. They are going to be dimensioned for the traffic that demands that low latency shortcut. And so automatically, the network is going to route the traffic that is delay sensitive over that shortcut. And then in between, there is another type of latency service that is available in this 3-tier, which is, it's a minimization of the cost, but with a bound of delay, which is to say, as much as possible, take the lowest cost, but make sure that it never exceeds that bound on delay. And so that is shipping and deployed. And again, if you look at it, you wonder why the IP technology has never done this like 20 years ago. I mean, it's obvious from a business viewpoint. So part 1 of the book issued 18 months ago, and part 2, which is on traffic engineering, hopefully is going to be issued at the end of March. It's a struggle. It's really painful to write a book, so I hope we had good feedback on part 1, but I can tell you it's part of the journey to write it, because to have the memory and to share it, but it's really painful. So I hope it will be good quality. But part 1, we had a lot of good feedback. Okay, now I have a few slides, which is the talk from 2015, in order to remind you what is segment routing. So I already introduced it a lot with the beginning, so I'll go a bit quicker here. So segment routing is about source routing. The source chooses a path and encode it into the packet header as an ordered list of segments. To start with, the list of segments will be MPLS labels. I'm going to have different Lego blocks. The first block I'm going to use to build my houses, etc., is called an IGP prefix segment. If I am in the core of the domain, I'm allocating a global label 16005 which everybody will know means this is the IGP shortest path to 5. And this, the IGP takes care of. If the network changes, if a metric changes, etc., if a node goes down, the network, the IGP, recomputes, and all the people, all the routers, they know 16,005, that direction is the shortest path. Me, as the controller, or as a source in another domain, now I know. If I want to go through the core via using the path to 5, I don't need to go and program all of the devices with an entry that is only for me, which is a very unscalable way to think. Rather, I'm going to build a segment, a source-routed policy that I will encode into the packet, where at some point I'll have a label that says 16,005. And that label will become the top label at some point in the core, and it will ensure that the packet goes to 5. That's the idea. Now, the second block in my Lego game that we are building up together is called an adjacency segment. Again, the IGP is going to take care of it. Every time that the router finds a neighbor, is going to associate with it a local label. The previous one was global. Everybody recognizes it, but the adjacency is local. Only node 2 knows that 124 label means go to 4. Why is it important? It's easy. In this drawing, the link between 2 and 4 is very thin. It means that's a bad link. Maybe it's a shortcut, but it has little capacity. So typically, it will have a very bad IGP metric. So it means that the network will not use that path. But me, as a policy, as a source-routed policy, I might have some latency-sensitive traffic that I want to force through that link. And so I need to go beyond what the routing would do. I need to force it, and the adjacency segment is that Lego block. I'm going to use it to force a path that otherwise the IGP would have not used. Let me explain it in a different way. If I would like to go to 4, I could, via the link to 4 coming from 1, I could not use the global segment 16,004, which in our illustration typically is the global label to 4. Why? Because from 1 to 4, the shortest path would have been 1654. It's based on the IGP metric. It would avoid that shortcut. But if I want to make sure that I go to 4 via 2 and the link to 4, then I would use a label of stack of 2 labels, 16,002 to go to 2, and then 124 to go through the link I chose. And this, I do it without state, because the program is in the packet header, not in the fabric. My third brick in my Lego game is the peering segment. It's very easy. Every time that BGP establishes a peering session, he allocates a local label that is called a peering segment, and this is advertised to the controller. And it says, hey, maybe that peering is again going to be having a very bad cost. Like you can advertise it with, let's say, AS path prepending, and there are many techniques to say, yes, I have that peering point, but it's not the one I want to use. Maybe it's because it's also more expensive, but it's actually a shortcut for some traffic, etc. Again, having a segment associated to it will allow the controller to basically steer some specific path that need to have that peering link through that peering link, even if the network as a whole thinks that this is not the shortest path. Here is the magic element of the solution. It's a segment routing PC. The segment routing PC has basically 2 elements. A database that is multi-domain by design. He pumps the information from all of the domains of your network. That's, let's say, the orange part of my segment routing PC logo. And then the brown part is the algorithms. And this, I always stress, it's segment routing native. When I started the project, it was one of my, let's say, not worry, but one of the key aspects of the research where I place people on. Because the way to compute path is completely different from RSVPT. Why? RSVPT is basically a descendant, a child of ATM family. And it's not to say anything bad. It's just that we need to go back into the 90s And in the 90s, the big ISPs, they were doing the traffic engineering with ATM and frame relay underneath. Obviously, they saw the speed going up. They wanted to compress the layers, get rid of ATM frame relay, but keep the same paradigm. So what the MPLS team did at that time, it's again brilliant at that time, is they said, okay, ATM frame relay goes away, but the technique needs to stay in. So they built RSVPT as an ATM frame relay paradigm. And I explain it to understand the difference between segment routing and the previous architecture. The RSVPT paradigm is based on ATM frame relay. What does it mean? It's based on a circuit. What is a circuit? It's a point-to-point non-ECMP path with state at every hop. This we don't want. It doesn't make any sense. I mean, historically at that time it made sense, but if you are in 2015 or 12 when we start the project, makes no sense. We're now in an IP-only system over DWDM. There's no longer any layer in between. There are many ECMP paths between A and Z. Building circuit is completely nonsense, because then in order to have the ECMP, you need to build many circuits and you need to load balance over the circuit. So we need to deal with IP ECMP aware path. But then all of the algorithms that existed were broken by design, because immediately they would basically look at the problem to find as an outcome a non-ECMP circuit. But this is not what we want. We wanted an outcome, a solution of the traffic engineering problem that is maximizing the ECMP path, because that's the nature of IP. You want to load share as much as you can. So all of this traffic engineering algorithm had to be rebuilt. And that's what we did in 2013, 14, 15. That's the bulk of the research from our side in these years. Now it's shipping for a while, since 2015, and this is the so-called segment routing PCE. The beauty we have with this, I don't have the time today to explain it, but again, there are two instances of segment routing from an SDN viewpoint. If you are in the web OTT world, you control your problem. You have data center to data center traffic. The majority of your traffic is traffic that you control. You basically, it's like if you have a dam and you open the gates here and there and you basically schedule your workloads, etc., to use your capacity. You are in control. If you are a service provider, you are not in control. If the bank sends traffic, you need to transport. You cannot say to the bank, hey, shut down the dam, you will send it tomorrow. No, you cannot. So fundamentally, it's funny, but often people forget this. They say, I want to do like Google, but maybe is it the same problem? And my view is that there are two different problems, but the solution, segment routing, supports both, but in a salient different way. If you are in the control world, more like what you would find in web OTT, the segment routing PC becomes like a god, because he controls, and he controls traffic, he controls the schedules of workloads, etc. And so he is the one programming the network. Typically in that world, they also build a controller themselves. And so the segment routing PC that you see, this is, let's say I can say it, rarely it would be a vendor, it's their own smart development, etc. If you are now then in the other problem, you don't control your workload, your traffic, etc., but you need to create SLA policies through your domain, then it's the segment routing PC that we build. Why? Because there it's the network as a whole that is going to react to VPN-based policies to ensure that the requirements from the banks, from the customers are going to be instantiated. And that's what I will explain later on. Okay? But the two models have been deployed. So how do I do an end-to-end path as a list of segments? Let's say that an application as a VM or a container, or a router that is an ingress PE of a VPN in front of a bank, has subscribed a low latency path from, let's say, the DC, but it would be the same if this is an access link, up to, let's say, a peering point to another site on the right. And so we see it's multi-domain by nature. The segment routing PC, he sees everything. He sees the left domain, the middle domain, etc. He has all the information, and he finds out that really the low latency path is to take all the ECMP path in, let's say, as in my document there, data in the data center. So I want to load share in the data center, but I want to specifically exit at node 1. Then in the core, I absolutely need to go to node 2 because I'm going to force my way into the low latency shortcut to 4. And I'm going to exit via the peering link to 7 at 4, which is normally not the preferred one. This is not the shortest path, but I know that I want low latency, and so that's the one I'm going to prefer. So that's what I want to realize. So this is the outcome of the native segment routing algorithm. And then I need to express it with segments. And in segment, it says 16,001, which means shortest path to 1 with maximum load sharing. Then shortest path to 2. Then force my way through the link 1 to 4, so 2 to 4. And then force my way on the peering link 4 to 7. And you say this does not require any per flow state in the fabric. The only one that is seeing the flow is the router 11, the top of rack, the ingress PE, the thing that is in front of the flow. It recognizes the flow, and then it encodes the policy on the packet header as a label stack, and the network is stateless. The network really has a simple thing to do. In the data center, he only needs to support 16,001. If the data center change, he updates the shortest path to 1, and the same in the core. And so all of the blocks becomes now isolated. Another aspect that I forgot to explain before on let's say, the philosophy of segment routing, I said interdomain was my day one objective. I wanted to have it interdomain. What I said, one difficulty is the notion of, let's say, route leaking. The second difficulty is there was absolutely no SLA-based interdomain deployment. But the third difficulty that again, everybody would forget. But when we come back to it, then we see, yes, indeed, it's so complex. In the previous architecture, what is fundamentally difficult in interdomain is that because at every domain boundary, you have to reclassify. You see, because in the packet, you have no indication of what that thing wants. So you have to reclassify it. And here go super complex DPI or 5-tuple access list, etc., which you need to, so it means state in the fabric that you need to control. So you need a big automation system, Instead of going for brute force, there's another path. Just don't do state in the fabric. Just put the program, and that's really what we call network programming, in the packet header, okay? Now, if you look at that example, and that's basically the attacks that came in 2013, and is to say, it will never work. I mean, you see, I'm going to have, let's say, 10 labels, but there are many solutions to this. First, as a living proof, we deployed it, so the hardware can do this. It's not difficult to push 5, 6 labels on a packet. And on the other side, from day one, we were saying that there are obvious scalability solutions to this. And it's not only that you want it for scalability, but you want it for routing scalability, for churn. And I'm going to explain it because it's a very important concept. It's a bit technical, but just focus on the philosophy of it, which is the scale and the opacity, and so the control plane churn protection. Instead of expressing my end-to-end policy as these labels, where, if you wish, a bit the problem of how I explain it here is that the top of rack there, he sees the whole list of segments as an operator. And let's say you are the operator of the core. Would you really want your colleague in the data center to see your label 16,002 and 124 and your label 147, that is your peering point? You don't need to give that visibility because maybe you will change it, or maybe every time your network change, these segments would have variation. So maybe you would like to have something that is more opaque to it. And by having the opacity, it means that anything you change yourself is not going to be seen by your colleague, but still the macro SLA you provide is stable. And so that's what the binding segment provides. The segment routing PCE can basically decompose an end-to-end interdomain policy into per domain policy. And so here, the segment routing PC would say, hey, node number 1, someone will need to write through you to go to 4 via a certain policy. We see this as recurrent. And instead of having everybody stay the full segment list, we're going to build an intermediate policy that will be referred to by all these people. This way it will scale better, they will have less labels, and there will be opacity. And so the segment routing PC contact number 1, and this operation is much more like a web OTT. It's the segment routing PC that takes the initiative and say to the router, hey, router 1, build an entry in your data plane that is going to push 16,002 and 124, which is basically the low delay path through the backbone. Bind to it a local label and tell me what it is. So it's a local label, node number 1 picks 1, and let's say it's 200. So node number 1 replies to the segment routing PC and says, hey, your core policy, it's summarized by one ID 200. Come at me with 200 and that's what you get. That's your opacity and that's your scaling simplification. Now, the segment routing PC can reply to the top of rack in a much better way. He says, go to 1, which is inside the data center, so that's a legitimate segment. Then take the binding seat 200 at node 1, which is a one label expression of a complete backbone policy, and then exit at 147. Okay? So this is the binding segment. So in a summary, it's interdomain by design. It's stateless by design. Obviously, you get the scale. A huge approach in segment routing is that we started in 2012, we end 2009, so 6 years and a few months. We have not invented, designed any protocol. And I was 2 weeks ago at LinkedIn, where one of my former team members is, and they invited me for a public presentation. So, and it was funny because I had forgotten it. Within when we do meeting inside Cisco, I'm a bit demanding with the team, and if they come up with proposal, cut. That's cut. The idea is we want to remove things, not add. And that's a metric of success. We have not defined any new protocol. That's a metric. That's what we want to do. There's no, in my view, there's no need, because you have ISIS and OSPF, you have BGP, then we need to add performance monitoring to have visibility into the network. Then we have BGP-LS and YANG to get the visibility, that's it. The rest, we just need the data plane to encode the source routing. Okay? So drastic simplification. There are now, 5 years after, numerous networks that have no longer any classic MPLS control plane. LDP is gone. And it was a mistake. And again, it's not a critiques, because we know why they did it in 1996. There was a good reason at that time, but not now. So this is gone. RSVPT, again, there was a good reason at that time. Excellent engineering, it's not to complain or say bad. No, but it evolved. And so they are now, it never was very much deployed, but they are. The prospect is now, in my opinion, null for RSVPT. Automation, TI-LFA, SR native algorithm, the PC, all of these are examples of completely automated solution. Per-link delay measurement. So that was my introduction. I guess where I am in time. Being a bit slow. But I was asked to make it wide. So let me hurry up now and say, so this is what we shipping last in January, and what is deployed, what we announced with Vodafone. So on a per-link basis, I just need to do delay measurement on the interface, and I'm going to trigger performance measurement. So every 3 seconds, I'm going to send a probe, and that probe is going to be repeated, and every 30 seconds, I'm going to compute the minimum, the average, the maximum, and the variance. So there are 2 aspects of that measurement. First, the minimum. The minimum is what I need from a traffic engineering viewpoint, because it gives me the propagation of the light on the fiber. This is basically giving me the length of the fiber. The fiber doesn't grow, doesn't decrease, it's stable. That's what I need from a routing viewpoint. Why? Because my low latency traffic is also going to be classified as a DSCP color that goes into the priority queue. I'm not going to have any buffering for this, so the only thing I need to minimize is the length of fiber. So what I want is the length of fiber is the minimum. So that's out of the measurements. A part of it, I filter it, and I only give the minimum to traffic engineering. That's what I'm going to work with segment routing. The other part, which is the average, the maximum, and the variance, this is purely for diff serve operation. So this, I telemetry it to the controller for the operation of the network. So that's the way it is. The minimum is going to trigger the flooding into the routing protocol so that the whole network knows about the variation of the low delay path. And you could tell me, but why do you need to continuously measure this? As you said, the fiber is not going to change. Indeed, the fiber is not going to change. But underneath your IP, you have your nice colleague from the DWDM rings. And you all know that they rarely call you when they do a change. And a typical issue of the IP operation team is that they are a bit blind into what the colleagues from the, let's say, the flow under are doing with the DWDM switch. Now you see it immediately. Because when the DWDM team change your routing into the ring, you know you're no longer taking the shortest path, but you take the other side of the ring. And what used to be 2 milliseconds is now 15 milliseconds. You see it immediately. You see it immediately, which is a great gain from an IP operation viewpoint, because then you can talk to them and say, how long will it say, etc. Visibility, operation. But then if you have low delay path on the network, now segment routing kicks in and may basically compute the path from A to Z, avoiding that ring, because unfortunately on that ring, we are taking the wrong side of it, okay? So that's the idea. And also, the beauty is that it's entirely automated. The solution before was to hard key these delay metrics via the T metric, but obviously then you don't catch when the DWDM ring changed. How do you use this? There are two ways to use it, and that's what I'm going to explain. So the first part is the segment routing policy. This is basically where I am on an ingress PE, and I'm going to say, hey, I want to go to Oslo, for example, low delay. And so the ingress PE has all of the native segment routing algorithm. He sees the entire database, and he's going to say, I cannot take the shortest path to Oslo. This is not the low delay path. I need to first go to Stockholm, and then from Stockholm, I'm going to Oslo. This is an outcome of the left side of the slide. This is when we do a segment routing policy. We have the declaration of an intent. I want a low delay path to somewhere, and the router automatically computes whether he can take a single segment, the segment of the destination city, or whether he needs to insert waypoints, a bit like when, and the intuition was this. I was driving to Rome, and then I thought, oh, why are we not doing the same with traffic engineering? That was the intuition. Again, it was not in the office. So, and so it's the first way to do the traffic engineering. We have introduced last year, and this is what Vodafone explained it with us in January, the Flex Algo. What is the Flex Algo? The idea for the Flex Algo was, again, the first presentation in October 2012. It was there. The slide at that time is that you have these Lego blocks. And up to now, you have seen that what we are playing with is that in a network, I'm basically building paths on the basis of blocks that are the shortest path to Stockholm, the shortest path to Copenhagen, the shortest path to Oslo. And if I don't want to take the shortest path to Oslo straight, but I want to take another path that would be as expressed as first go to Stockholm and then Oslo, I do it. But look at what I am doing. I'm always building a policy, an intent, using the same type of bricks. These bricks are the shortest path according to the IGP metric. Immediately, we can think and say, why am I mean, if I look at the Lego block, all the bricks are not the same. I have yellow bricks, I have blue bricks, they are long, those are tall, etc. So why am I not building into my solution other bricks? And so if you go back at 2012, you see the first IETF draft. In the segment, we introduce an algorithm. And this is FlexAlgo, is the instantiation of this, and I'm going to explain next here, is basically we're going to add in the IGP domain other bricks, where the IGP is going to always maintain two shortest paths. The shortest path to to Oslo, according to the low cost, but at the same time, the shortest path to Oslo, according to the low delay. And ISIS does this for you. Simply, Oslo is one loopback, but to that loopback, I associate two global labels. For example, 16,000, if Oslo is node number 1, 16,001 will represent the low-cost path to Oslo, and 16,011 will represent the low-delay path to Oslo. The ISIS will maintain this. And so now, if you want to, for example, instantiate an interdomain path where you need to somehow exit at Oslo and then go through a metro region near Oslo, all what you need to do is to say 16,011 and then where you need to go. You no longer need to have multiple segments to build your low delay path, okay? And that's the right path is where we use this link measurements to build other types of segments, flex algo segments. Why are we calling them flex algo segments? It's in order to stress that you own the definition. It's not defined by Cisco, it's not defined by the IETF. When you're going to instantiate this, you're going to say, me, in my deployments, I want ISIS to compute these segments according to this algorithm that I will define myself. And so you can completely customize your routing protocol. This I skip, and I go to the FlexAlgo. So that's FlexAlgo. You customize it. You typically define two things. What you want to minimize, either the cost, the T metric, or the delay. And then you say what you want to exclude. Link colors, that are called affinities, or SRLG. Two operators may instantiate the same FlexAlgo 128 for very different things. You own the definition. Once a node is part of a FlexAlgo, there's a very little extension in ISIS to say, hey, I'm part of that FlexAlgo. And when you announce a prefix segment, there's, from day one, this field algo that is saying, hey, that label, that global label, it has to be computed according to that FlexAlgo. So one instantiation of this, and you don't, yes, you see it better there, is basically to build, again, something that is so obvious but was never done before, dual planes. How many times banks come to you, government, army, etc., and they say, I want two disjoint paths to go from, let's say, that city to that city. Obvious requirement, extremely difficult to do before segment routing. Here, very easy. I do two planes. So I have the algorithm 0, which is the IGP shortest path, and then I have a green plane, Algo 128, and I have a red plane, Algo 129, where the path is going to be constrained to the green plane or the red plane. And I will explain this in detail in the next few slides. So I don't need to add any IP address. Again, this notion of simplicity and minimalization, so cut. We don't want to add things. So you have a single IP loopback. Underneath it, I'm going to associate multiple global labels. And to these global labels, I'm going to associate an algorithm. So 16,009 here is the global label to go to 9 according to ISIS on the global topology, while 16,809 will be the global label recognized by everybody in the green plane to be the shortest path to 9, only restricted to the green plane, and so on. The definition of the algorithm is critical. Everybody needs to have the same. There are two ways to do it. Either you configure it on every device, obviously using NSO or something like this, or you have two routers that advertise the definition for the domain. Anyhow, there is a built-in mechanism inside the product that checks that everybody has the same definition, because otherwise there would be loops. And if there is inconsistency, then the flex algo is disabled. Computation. Computation is like super simple. It's always the same. First, if I am a node, I never compute what I am not part of. So if I'm not part of flex algo 128, I don't compute it, scalability. Then I check whether everybody in the algo 128 agrees with my definition of the minimization technique. Yes, okay, then I compute. First thing, I prune the topology. I look at the entire ISIS topology and I prune all of the nodes that do not claim to be part of algorithm 128. I prune them. Then I look at my definition of the algorithm and it says avoid SRLG 200, avoid the links blue. I prune all of these things. What I get is the topo 128. Once I get the topo 128, I simply do a shortest path, a Dijkstra algorithm according to the metric that you associated with algo 128. So let's put this in practice. This is my example. This is my topo 0, that's what ISIS see. This is my topo 128. This is my topo 129. This is the shortest path to the 16,009 according to algorithm 0, that's obvious. It's basically if I assume that all of the links have the same ISIS cost, ISIS is going to load share in a maximum way. This is the shortest path to 9 according to algo 128. Immediately, ISIS does what it needs to do, is to say, hey, it's the shortest path, but in the topo 128. And this is the shortest path in the topo 129. And that is flex algo. Okay, so obvious. TI-LFA, which is this automated fast reroute technique, which is optimum. So it's in advance of the failure, we compute the backup path that should be taken if the link fails. We install it in the data plane in a way that is prefix independent. When the link fails, in sub 10 milliseconds, in sub 20 milliseconds, we enable the backup path and hop all of the traffic go. So overall, when you do the measurement, it's like 20, 25 milliseconds fast reroute technique on a per prefix basis, so optimum from an IP viewpoint, 100 times better than RSVPT used to do. And totally automated. It's ISIS that computes it. This TI-LFA that has been shipping since 2014 immediately is reused for each algo. So let me take it back. This is the shortest path for 16,009. Immediately in advance of the failure of the link 528, 5 pre-installed in his data plane that if he detects the link failure 5.8, immediately is going to switch the outgoing interface of 16,809, 6,909 to no longer be a load sharing 8 and 6, but only using 6. Why? Because he knows that this is the topology and the optimum backup path in the constraint of the topology is this. Note that it would not be the case, it depends on the metric, but it would not be the case in the algorithm 0. Because in the algorithm 0, if you take a look at 5, it would be the case in this example, but I could construct other examples where it would not be. When 5 precomputes the backup path, it could be that 5 would use the link via 1. And which means, because in algorithm 0, there's nothing that precludes you to do this. 1 is also part of the topology. But if you are in the algorithm 129, the operator said, no, I steer the traffic into the red plane. If I did it, I also want you to protect it in the red plane. And this, you get it for free. It's automated. Why? Because it's a notion of mathematics, is that it's a recursion. We reuse the exact same algorithm, but within the constraint of the flex algo that you define it. And this, immediately you got it, and this is what is deployed. Now, where am I in time? Okay. Why did we productize flex algo only in January 2018 and not back in 2014? For multiple reasons. But one of the reasons is that if I have a block, that block, obviously you think, wow, first time I have like multiple ways to go to Oslo that is completely automated by my routing protocol. That's obvious. Why did we not start segment routing with this? Because the idea is that you want to do inter-domain policy. You want to have an inter-domain solution. And so in order to have an inter-domain solution, it means that, yes, I have great and powerful blocks with this flex algo, but they are restrained to one domain, the ISIS instance. If I need to cross two domains, I'm blocked. I have a great way to get to the border, but I cannot get somewhere else. So that's why we started with the segment routing policy, because that's basically the solution that gives you the inter-domain reach. And that's why we started with what is called ODN-AS, On-Demand Next Hop and Automated Steering, which is the automation of all of the traffic engineering and the inter-domain traffic engineering solution. And that's what I'm going to explain next. I'll come back to this later on. Cumulative metric bounds, I'm going to skip it. Once you have understood what we do, this is basically the explanation of the three-tier latency service explained by Vodafone. It's basically up to now in my presentation, you really understand that I can do a minimum cost. This is my prefix segment according to IGP metric, and I can do a minimum delay. This is the prefix segment of Oslo according to the real-time measured per link delay. But then there was the third solution that Vodafone explained with us, the minimization of the cost, but with a delay bound. And you'll have the slides. It is shipping. You can look at it. It's relatively easy to understand. There's a video as well to see this. Now, this is the ODN-AS, and I will end MPLS part with this, because it's very important. Let's say that I want to go to 4, and I have the global prefix segment according to ISIS cost that is 16,004. And let's say that in this deployment, I don't have flex algo to find a low delay prefix segment of 4. So I'm going to build it as a list of ISIS best effort segments. So my policy at node 1 is going to be called 4 green. 4 green means low delay, 4 low delay. And so in that policy, I am going to state the intent. I want to compute the low delay path, the min delay path to 4. The native routing protocol, the native segment routing optimization algorithm kicks in and finds that 16,004 is not the low delay path, because the link 1.3 is a very bad delay, but the low delay path to 4 is to go to 2 and then to 4. So it's the MPLS stack 16,002 followed by 16,004. Okay, that is the outcome of a segment routing policy. This is the outcome of a native optimization with segment routing in mind. But still, for you, you would not be happy with this. Because why do you care about being able to state a policy? You don't care. You want to apply it to traffic. And you want to automate the application of that SLA to the traffic. And so that came up in a taxi ride in Rome. Always funny to remember where it came. The idea is to say what is central to operators and large enterprise is that all your services are carried as VPN, L3 VPN or L2 VPN or pseudo-wire, but that's the basic of your business process. And so the granularity of the SLA instantiation is much better expressed at the VPN layer than underneath. So what we offer, and this is shipping since 2015, widely deployed, is to say to the operator, reverse the thinking process. When you had RSVPT, you had to create your tunnel, and then you had to do static routes, policy-based routing, very complex things to get your traffic onto it. Here, it's the other way around. You focus on your VPN, and you color them with BGP Color Community. And for example, the VPN customers that subscribe the low delay path on the operator, like for Vodafone, it's obvious you can understand what they are doing from this, is that it's easy. That bank wants low delay, you color it green, and that's it, finished. Because when the ingress PE number 1 receives the VPN route, he sees that the next stop, the VPN next stop is 4, but the BGP route says green. I cannot use IGP best cost. I need to use the policy green to the next stop. What is it? And this is the only thing you need to have. All your ingress PEs, they only have templates, which says green is low delay, blue is the blue plane, red is the red plane. So you have, let's say, 2, 3 profiles that always the same, where you declare the human-based intent. And so when the ingress PE, then it's entirely automated, when the ingress PE receives a VPN route, he's going to basically see the next stop and he looks whether there's an SLA color. And if there is an SLA color, BGP calls TE inside the router and says, give me the policy that goes to 4 green. And then the BGP route, the VPN route, the pseudo-wire route is automatically installed on the segment routing policy. Okay? So that's exactly what is shown here. Node 4 advertised 2 BGP routes, here for the internet, but obviously it's applied to VPN. It makes actually typically more sense in the VPN context. 1/8 is announced with next stop 4. No color, it means best effort. 2/8 is announced via node 4 with the color green. And when 1 installs in his data plane, he's going to install 1/8 via 16004, because it means this is the best effort path, the low cost. And he installed 2/8 on the policy green, which is 4. That's what we called automated steering. It's the automation of traffic engineering. You completely abstract your problem as a BGP coloring technique. You color your route, and then the fabric, that's what we call the unified SR fabric, basically builds it. Now, I will quickly try to go back, and then I will stop. It's here. See, that automation has been thought immediately for interdomain. So when these 2 domains exchange a VPN route, 9 announced 2/8 via noun with the minimum delay, the VPN route reflector relays it, 0 receives it. For him, whether it's intradomain or interdomain, doesn't care, it's always the same. What basically 0 is going to say is that, that VPN route is green. What green means? Low delay. 9 is not in my domain. I am not able to compute. Automatically, I make a request to the segment routing PCE controller. And then the segment routing PCE has a global view. He computes the seat list. He gives it to me. I install it in the data plane. I install the VPN route on it. That's entirely automated. And if that policy can be instantiated with blocks, with prefix that are flex algo, obviously we'll do it because it will lead to a shorter segment list. And that's exactly what we would do in an interdomain deployment that leverage the flex algo solution. And this is shipping since last year. Okay, so I'm going to stop here for SR MPLS and give you a little of you'll have much more, but we covered what we needed to cover, in my opinion. So it's the philosophy. Okay. SRv6, we have to present it with a lot of humility because SR MPLS, it's successful 5 years after. The deployment speaks for itself. There was a lot of work from the lead operators, etc., that enable it to happen. SRv6, we are earlier into the journey, and the journey is difficult, comparatively more difficult, because obviously we require new hardware. Here we need the SRv6-based hardware. However, I say it immediately, we just announced our first deployments, and SoftBank, with whom always it's lead operator based. we've been working over the last 2 years to get to this milestone. So when you see this presentation, look at it again with this notion of philosophy. What does it mean? Yes, it's novel. Yes, it's quite, how to say, powerful, but are there indications of realism, of pragmatism, of reality? Yes, we're shipping this product. Yes, it is deployed. When we announced the deployment at SoftBank, I immediately indicated that actually there's a second deployment already done, but the public communication will come later on. And we're working on other designs. So we do see enough to know that this is going to happen. And especially, you always need to have a business reality with it. And the business reality is 5G. And if you look at what 5G means in terms of scale, of control, of interdomain, scaling number of endpoints, IoT, etc., it's kind of clear that SRv6 will happen because of that 5G demand. And there is enough business investment to basically make it happen, okay? But I again said it's extremely powerful, and so you might at first think, ooh, that's for 20 years in the future. No, it's happening. And the summary is that simplicity prevails. You cannot fool simplicity. It's like the free market, it's like Adam Smith, it finds its way. Especially if you study the proposal in detail, you will see that it's only that simplicity prevails. It's absolutely not the case. It's not only that it's more simple. It's actually providing much more scalability and much more functionality. And that is really what should impress you. It's the fact that it's funny, it makes things simpler, but at the same time more powerful. As always, lead operator is key, and that's the kickoff, January 2017 at La Sapienza University. We always have lead operators and lead academic because the research is always critical in part of the project. And so that's the kickoff, 4 full days. So when we see, sometimes at the ATF, people say there's a lot of, let's say, aggressive mentality, and people say, all of these people, maybe they are not involved. Well, I can tell you it's 4 days. It's 9 to 6 every day in Rome. Usually in the evening, there were a very good restaurant. I love Rome, and so I picked very well the restaurant. So, I mean, it was hard work. And anything we discussed during this week in January 2017 has been done. At the outcome of that week with the lead operators, we basically decided how we would do it, who would be the other vendors we would approach on the basis of basically their needs in terms of deployments. And we've always done what we committed. For us, all of the transparency from a standardization, from an ecosystem, is basically part of the contract we made with the lead operators. And so what is the idea? And I'll focus on the idea here. We're going to no longer use the MPLS data plane. We're going to focus on IPv6 because IPv6 gives us the reach. It's 5G, it's human population, containers, IoT. We need that IPv6 reach. But if you look at IPv6 itself, obviously it gives me my reach, which I need, so it will happen, but IPv6 is weak. It's like IPv4. It gives me best effort connectivity, but doesn't change anything from the address length. So I don't want to redo what I did with IPv4. All of these hacks above it and below it. If you look at the longer presentation, you will see a slide where we detail this. And you really see this, it's the principle, is that if you look at IPv4, there were lots of hacks beneath, there were lots of hacks above. And here with SRv6, we say, let's try to find a minimum element that we need to do to IPv6 to make it strong, that it deals with its problems himself, so that you don't have the need for hacks above and hacks below. What you want to have below is Ethernet. What you want to have above is TCP UDP transport. But you don't have a pseudo routing layer on top, and you don't want to have a pseudo routing layer below. That is the idea. So we're going to say that the 16-byte pattern, which normally is called an address, is now called, if it's a segment, if it's part of SRv6, it's called a network instruction. The first part, the left part, is like typical in routing, it's a locator. So typically, if you think the /64 is a routed locator. It's not bound to strict numbers like 64, 64. You can do whatever you want. It's always that idea of like you in control, but it's easy to explain this way. Let's say that the right side 64-bit, it's a function. Think about compiled code. It's basically a compiled, it's a pointer into memory to a function. And when you compile the code on a server, implicitly, the function is local to that CPU. But here, it's a compiled pointer to a function in the network. And where you execute it is the locator. And that's it, you get it. That's why John Leddy, who was at Comcast at that time, it was the VP of the network architecture of that time, was very influential in the first years of SRv6. He had a great talk to say, it's to represent the network as a computer. And that's really the idea. That's why that the NFV, the service chaining, all the work we are doing with Kubernetes now is totally foreseen. It's not like something we discovered now that we're doing. No. Back in 2013, we wanted to do it, but it's always, you have to build things in the right way. First, we have to lay out the underlay, the overlay, and then now we're working with Kubernetes, etc., on the NFV side. So I'm going to build a network program, which is like compiled code, that is going to refer to functions into the memory of different CPU over the network. And I want a network program, I don't want one instruction. So I'm in the packet header, I'm going to have this extension header where I'm going to place my program, which is simply a sequence of network instruction. Go there to execute that function, then go there to execute that function, then go there and execute that function. And so I'm going to have in the destination address my first instruction, go there to execute that function. And in the segment routing extension header, I'm going to have the next instruction I need to execute with a pointer that tells me where I am in the program. I'm going to have a tag because it's obvious that it's always more scalable to have group-based policy. I don't want to have access lists that recognize 5-tuple flows to implement who can talk to whom for microsegmentation. Much easier. At the ingress of the network on the top of rack or at an ingress P, I color the tag, let's say yellow, it means it's a certain type of customer. And then when I am in front of my data center, I have very simple contract. Yellow can go there, yellow cannot go to green, yellow can go to blue, but blue cannot go to yellow. You know group-based policy, that's what we do there with the tag. And then we have the global arguments. The global arguments are basically metadata, where you have the user identity, you have performance information, you might have credential, etc. And obviously, we did this, the first implementation was done in 2013. Dave Barak, which is a brilliant data plane engineer, was very kind to actually build the first implementation. And if you go back into the history of our presentation and our ITF document, the first SRh proposal back in 2013 was different. And so we learned from the first implementation, and that's how it became like this. And so it is optimized for two worlds, and it's super important to understand it. Because if someone doesn't understand it, he would see, oh, these people are crazy. No, it's not crazy, it's well thought. So the first part of the extension header is optimized for hardware processing. This is what the routers will do in the data plane for underlay and overlay operation. The bottom with the metadata is there for the CPU world, for the NFV world. This is where different NFV applications are going to put, for example, user identity. And we have already some demo with partners where we see that the DPI technology recognize application, put into the metadata the type of application, so that later on other NFV do no longer need to do DPI, but basically act on the basis of this information. And this is demonstration that are on video. Where am I in time? Unfortunately, I don't have the time to do much more than this. I would refer to you, this is the talk I gave at LinkedIn 2 weeks ago. The video will be on segmentrouting.net. I guess I need to remember to send them an email to have the link, so I'll put the link, segmentrouting.net, in the conference. It's a 15-minute talk, so if you're interested in learning more about SRv6, don't hesitate. I'm going to skip a bit the examples because in essence, it's the same as SR-MPLS, but expressed with network instructions. And the idea is that first, simplicity. Protocol elimination, no LDP, no RSVPT, no MPLS data plane, no L2TP, JRE, UDP, VXLAN. All of these are, that's why we have always academic people with us as well. And me, I like analytics. There's a notion of like analytical study on network layering. These are acts. If you look at it, it's acts. These things should not have been made as independent layers. They can be expressed simply in the IP layer. No GTP, no NSH. It's just what IP needs to resolve, IP can resolve. I'm not saying that IP needs to go into, let's say, the transport layer. This would be a mistake. But what IP as a network layer needs to do, it should do. Scale, we are often attacked. It's an aggressive world, and that's the way it is. And people would say it's crazy. I mean, if you go back like a couple of years, because we are supporting this at the ATF for a long time, 4 or 5 years. It would never work, the hardware cannot do it, etc. And the answer is the same as what we gave for MPLS. This is where we need to be lead operator based, use case based, and pragmatic base. And the deployment at SoftBank and the other deployment prove it by the practice. The real use case do not need 24 segments. And so there's no point to go around and scream, it will never work, they are crazy, that's marketing. No. There are many, many use cases that will work with just 1 segment or 2 segments. And this, factfully, the hardware can do it line rate. And then obviously over time we can do more, etc. But we can start, and there are obvious solutions like the binding segment to restrain the number of segments. And you will see in the future there are other brilliant ideas to basically drastically extend the power of SRv6. We'll talk more on this later. Now, maybe this, don't worry, I'm going to finish, is that again, from an analytic viewpoint, think about going back to IP, what it means. It's simple, but you get back to summarization. You can summarize. In MPLS, you cannot. And when we are in design sessions, and then we think, oh, damn, I could do this, but it's like 20 years backwards. We go back to IP routing, and there are obvious scalability advantage to be able to do longest match lookup. MPLS is a flat lookup that leads to route propagation, and so lack of scaling, etc. Here we are relieved from it. We go back to IP and we have a longest match. This notion of longest match summarization is going to give us a lot of extra scale. Further functionality, immediately when we designed this, we thought we wanted to basically prove that this was Turing complete. You can express whatever you want with SRv6. So we called a university, and we had a call with one of the mathematicians, and he said, well, obviously it's Turing complete. I mean, I don't want to work with you on this. I mean, it takes 1 line. As a network instruction can refer to any pointer in the memory of the CPU inside the network, that pointer may be a VM or a container. And the VM and the container is itself Turing complete. So obviously it's Turing complete. So the proof that this is Turing complete is obvious. But even if we would not use that argument to prove it, it is Turing complete. You can, because you can do go to, conditional check, etc. You can branch. This is a totally powerful network programming construct. I will stop here. The rest you can listen on the recording. This is totally tangible. We have proven hardware based on either merchant silicon or Cisco silicon. Multiple other vendors like Huawei, Barefoot, and SmartNIC vendors communicated on this. So it's totally true from an ecosystem viewpoint. Huawei announced on the mailing list that they have an SRv6 deployment in China as well. So you see, I think it's good. It shows that the ecosystem is healthy. Barefoot was the first for us to do an interoperability at July 2017. And we have released our first FCS image on on the Jericho-based platforms and on ASR9K with SRv6 ISS, SRv6 TI-LFA, SRv6 L3 VPN, and SRv6 OAM. And it's coming as well on the data center platform. So it's across the product line at Cisco, Enterprise Service Provider DC. And let's finish with this. It's a long journey, extremely huge amount of work. But we announced 2 weeks ago the deployment at SoftBank, and there's another deployment that has been done as well that will be announced later on, and there are other designs on the way. So it's the very beginning, but it's also an encouragement. If you're interested, we need lead operators, we need your involvement, we need your use case. So I always finish by this, is to thank the lead operators, but also encourage you to start early, because you don't need to tell me you're going to deploy in December 2019. I don't care when you will deploy, and maybe you will never deploy. What is interesting is what problems do you see, what intuition do you have that you think it would help you, because this, you know better, okay? So thank you, and that's why many thanks for the invitation.